All right, let's quickly continue. Model 5.2, still mixing processes and mechanisms 2. So let's continue. It's just a continuation of model 5.1. Here we'll look at solid particle suspension, solid particle suspension regimes, gas liquid dispersions, gas liquid dispersion regimes, liquid liquid dispersions, mean diameter of drops, then blending, mixing of powders and paste. Remember, we've looked at solid particle suspension, we look at gas liquid, look at liquid liquid, we look at solid liquid. So we're just going to look at the regimes, the different regimes that exist in all these suspensions or mixtures. So solid particle suspension. Now processes involving solid particle suspension in liquids. Examples are leaching, solid catalyzed reactions, crystallization. We've done crystallization in the lab, so you should be aware of that. Are often carried out in agitated systems. The role of agitation is to make available to mass and heat exchange for the surface. Therefore, all particles should move freely inside the tank. This is a bulk motion controlled process. Remember, we said the processes can be bulk motion controlled or shear stress or shear rate controlled processes. Now, the aim of agitation will be to produce a homogeneous mixture, to dissolve the solids, to catalyze a chemical reaction, or to promote growth of crystalline products from supersaturated solution. Now, there's what we call just suspension agitation speed, and that is given by the Zwittering. That is the equation here. This equation is important. We've explained all the parameters here. Just suspension speed, NJS. Mu is kinematic viscosity. G is gravitational acceleration. Rho L is the liquid density. Then B is the particle mass to liquid mass ratio, and so on. Geometric factor S. Everything here is explained. So if you are given values for this, you should be able to calculate, the just suspension agitation speed. Solid particle suspension regime. Now, when you come in solid particle suspension in a tank, there are basically 4 different types of regime. One is the incomplete suspension. And this one, some of the suspensions, will be resting at the bottom of the tank. Incomplete suspension. There's the second one, on bottom suspension. Most of the particles will be moving on the bottom. The third one is off bottom suspension. Now all the particles do not rest at the bottom. So this gives us just suspension regime. And this is a commonly adopted working regime. Because if most of the suspensions are at the bottom or incomplete, you will not get a good mixture. Then of course the fourth one is homogeneous suspension. So particles are uniformly distributed in the whole of the tank. Now gas liquid dispersion. Just like we talked about in solid particle suspension, we also want to look at what happens to gas liquid dispersions. So gas liquid mechanically agitated systems are used for processes where liquid mass transfer phenomena are involved. For example, hydrogenation reactions, chlorination, oxidation reactions, and so on. And the aim or role of this is to generate as much interfacial area as possible by disrupting the gas phase. Remember, we said that the gas bubbles are very difficult, to submerge in the liquid. So we must have to force that to happen. To disperse the bubbles throughout the liquid, keep the bubbles in the liquid for sufficient time, homogenize the liquid concentration, enhance mass and heat transfer coefficients. So to this aim, impellers that produce large stress, that is high velocity turbines, are the ones recommended. Now look at the gas liquid dispatching regime. At the beginning, A and B, we have flooding. Look at what is happening here. As the gas is coming in, you have these bubbles, and then gradually the bubbles will now start spreading. And then C, we'll call it loading. Look at it. Then D, you have complete dispersion. Everywhere the gas has dispersed. And then highly gas recirculated regime. That is the last. Look at everywhere now the gas has, entered everywhere. So that's what we call gas liquid dispersion regimes. At the beginning, it's just coming in. And remember that, as we'll see later, the gas must be injected just at the tip of the impeller. This is our impeller. Look at the rotation, the way the impeller is turning. So the gas is dispersing. If you come to B here, dispersion is increasing. You come to C here, it is increasing more. It has, loaded. Then when you come to D here, we'll say it has completely dispersed. And then this one is highly circulating. Now we'll go over to liquid-liquid dispersion. Liquid-liquid dispersion operations may be performed in agitated tanks provided by high shear rate impellers. Now, as in the case of the gas dispersion, still about interfacial surface. So the droplet size of the dispersed phase will depend on the degree of the agitation. So the more you agitate, the more you will disrupt the droplets, and the size will reduce, and all those droplets will come together. That is what we mean by coalesce or coalescence. Liquid-liquid systems are characterized by major complexity with respect to solid liquid and gas liquid dispersions. Liquid-liquid dispersion operations may be performed in agitated tanks provided by high-rate impellers. Now, as impeller action produces high liquid deformations as shear, in order to deform drops of dispersed phase and break them into smaller ones. The more you break them into smaller ones, the more the fluid comes together and then mixes as quickly as possible. Then there's what we call mean diameter of drops. Mean diameter of drops. And this is the main global parameter describing the characteristics of dispersion in liquids. Considering that the droplets are characterized by a dimension distribution, the average diameter usually adopted is the surface-based mean diameter, the Salter diameter. And this Salter diameter is given by this equation, where we have phi as the displacement phase hold up, and A is a specific surface area. Now we'll look at the correlation. Now several empirical relations have been proposed or used to estimate the mean diameter of drop of the mean drop diameter depending on agitation condition relevant to different mixing. We have the Rosten turbine. For the Rosten turbine, these have been used. The static kinetics mixers, this equation can be used, where of course D is pipe diameter, average fluid velocity, frictional factor, and so on. And WE is a Weber number, which we have met before. Now, blending, mixing of powders and paste. Blending is the mixing operation aimed to homogeneous two or more miscible liquids by agitation. Of course, most of us use blenders, and we know what we use blenders for. The blending efficiency depends on the global flow rate moved by the impeller, that is the bulk motion control. When that blending action is taking place, the entire fluid will be moving. That is what we call bulk flow. Many industries such as food, cosmetics, pharmaceuticals, plastics, and so on, they make use of these blending processes. Now, in this blending, it is direct experience. Direct experience is the main guide to selection of the best kind of equipment, predicting how well and quickly it will perform and what power consumption it will need. there is no, there are a lot of school of thoughts that have done a lot of predictions on this, but it is from direct experience. The more you work on blenders or work with blenders, the more you are able to predict. In fact, it happens even in our kitchens. Those who have been using blenders will know that sometimes it is from experience that you reject one blender, or accept one blender against the other. So for this, we're saying the same thing. All you need to do is, when you work with that, you can do a test. And when you do a test, you find out whether that is okay for you in form of a pilot plant study before you can now talk about, construction or securing for industrial production. There are specialized mixers and blenders for powders and pastes. If you check your material, we've been able to list different types of blenders and mixers for different types of pastes. Remember that most of those pastes will eventually have, be more viscous, that is high viscosity. So you need to use blenders that are strong enough to be able to carry out the mixing operation. Thank you very much. We've come to the end of Module 5.2. We've looked at solid particle suspension and their regimes, gas-liquid dispersions and their regimes, liquid-liquid dispersions. We have also looked at mean diameter of drops, and we have looked at blending, mixing of powders and pastes. I hope to see you in the next class. Thank you very much.